All right, let's get started doing some more examples here then. I am a little bit behind on grading, guys, so sorry about that. I'll get that done here hopefully in the next couple of days. I'm also working on finishing my final paper, so in the middle of doing that and running this class, so a little bit behind, my fault, but I'll get it done here in a couple of days. My inclination right now for the final exam, not sure what the last day of class is. I think something like the 7th or 8th. My inclination for the final exam right now will be to publish the test on the last day of class and then give you guys until whenever the final is due, whatever date the final would be for this class. I'll look that up and publish dates for you. But that should give you 4 or 5 days to work through the problems, because I understand you guys are studying and doing finals in other class, and some of you work and have travel obligations and such. So I think that's a fair way to do it. It'll be similar to the format of the last test, where you'll have a few multiple choice or fill in the blank things from the homework, and 3 or 4 that will be things that I will invent that I need you to write down, scan them in PDF or something and send it to me. And then I'll grade them as I can. So it should be no surprises. I know there's a lot of information since the second test. I'm aware of that. This is not going to be designed to kill you. This is more of a survey class. So I don't know that there's going to be a whole lot of focus on just one area. I'm just going to pick some interesting things from a couple of areas. So you might get one problem on rotational inertia and one on pressures or something like that. So nothing big, nothing you can't handle. So like I said, we were going to talk about Pascal's law. So remember Pascal's law, we're talking about pressure. So we have a couple of things that we need to know. We have a couple of formulas. We know that pressure is generally force per area. We know that density is mass per unit volume. We also know that there's a thing called static pressure. That's usually rho GH. There's a derivation for this that I'm not going to worry about. What this is, you can think of this as kind of the intrinsic potential energy of a fluid at rest. So it's a function of its density, acceleration due to gravity, and how deep you are in the water. And remember last time I talked about, let's say we have this infinitely high column filled with air. And that column has a surface area on the bottom of 1 square inch. And if this is on Earth and we go all the way to the edge of the atmosphere, then obviously there's some weight here. And that weight of that 1 square inch is the pressure of the atmosphere is 14.7 psi on Earth. And that's at sea level, by the way. So sea level is for physicists, for aviators, for sailors. Sea level is the level of the ocean, not to be confused with elevation. So for example, I told you the other day that Little Rock Airport is about 500 feet above sea level. Whereas if you go to the beach, you're effectively at sea level. So your elevation at Little Rock would be about 500, what we call MSL, mean sea level. At Daytona Beach, it's going to be 0. But we also generally, when we talk about height of something, we talk about height above the ground. So if you're standing on the surface of the runway at Little Rock, you don't think of yourself as being 500 feet up, right? You think of yourself as being at ground level, which your altitude is 0, but you're actually some 500 feet above sea level. Now, in terms of pressure, that's where this is going to matter. So if we're at 500 feet above sea level, this pressure doesn't really change that much. I mean, think about the height of this. This is the height of the atmosphere, so about 120 miles or so. So that's a lot of air. So if we go 500 feet, well, that's nothing, right? That's insignificant. However, if we go up and we measure our air pressure here at, say, I don't know, 30,000, then your pressure is going to be much lower because of this, right? Our pressure is a function of the density of air, the gravity, and the height. Now, the density is going to decrease as we increase altitude because density is mass per unit volume. For the same volume, there's less air, so the density is lower, and our height is going to get lower, right? Less stuff on top of us. So at 30,000 feet, our pressure is, I don't remember off the top of my head, I think it's like 7.3 psi or something. It's pretty low. So this is where pressure comes into play and makes a difference. This is also true if you go the other way. If you get into something that's much more dense than air, it doesn't take a whole lot of change in height to give you more pressure. For example, I'm a certified scuba diver as well. Every 33 feet of water is 1 atmosphere of pressure. So if you go down just 33 feet in water, because water is much, much more dense than air, it only takes 33 feet to give you 14.7 psi instead of 120 miles. So this is the big problem with ocean exploration as we go to the depths of the ocean. In deepest parts of the ocean, you're talking about 30, 40 miles down. That's a lot. It's a whole lot of pressure. It's enough that it will crush anything that we can build, which means that ocean life at those depths is really fascinating. Things that we haven't even observed. It's pretty cool. Anyway, quick review of pressure and what we're talking about. So I want to do a couple of examples for you. They're going to be kind of typical of what I would expect you to be able to do in the homeworks and on the test. So I just looked some of these up, by the way. So nothing magical here. If you want some extra practice doing this stuff, then you can just do Google search, which is exactly what I did. Just do a Google search for hydraulic equations or examples or Pascal's law examples, something like that. So what I found here is I've got a hydraulic lift with 2 different pistons. So let's draw this. So here's my standard hydraulic lift. Not to scale. Not an artist. So here's our two different hydraulic pistons. And we're going to assume they're circular. And so we're going to say that the diameter of this one is 60 centimeters. So you got a 60 centimeter disc platform there. And the other one is 5 centimeters in diameter. So if we say that we come along on the small side of this piston and we apply some force, and let's just say that that force is 50 newtons. Just make the math easier. So what I want to know, obviously, this whole thing, this whole cylinder here, this is full of some kind of fluid. Might be hydraulic fluid, might be water, might be air, might be nitrogen, who knows? But it's some sort of fluid and it's contained. So the reason this is important is because if this system is contained and we apply pressure here, there's nowhere for that fluid to go. So it's not going to leak out. It's not going to come out of the end of a hose or anything. So it's got to move. Well, if it's completely full and we assume a non-compressible fluid, so we're not going to worry about the fact that, yes, we could squeeze the water hard enough to make it a solid. We're not doing that. We're going to assume this is non-compressible. So that pressures get transmitted equally. And this is Pascal's law, right? Pascal law tells me that any pressure exerted on a fluid is exerted equally at all points in that fluid. So if I apply a force here, that implies that there's some pressure there. Call it force, by the way. So that implies that there is some pressure in the fluid. And so what I want to know is, well, how much force am I going to get out of this, right? So the reason we want to do this is a tool. This is a way to do some work, right? If I'm going to lift a car, for example, on a car jack, I don't necessarily want to go just by myself and try to pick the car up. Car weighs 2,000 pounds or so. That's going to be difficult. So I'm going to put it on hydraulic lift. I'm going to create this system. And then I'm going to press down with 50 newtons and I'm going to see how much I can lift. So how do we find this? Well, first of all, we look at the equations that we think we're going to need. We know that this thing is in equilibrium. We know that we have some pressure in the system. And we know that pressure is force per unit area. And because of Pascal's principle, we know that P1 has got to equal to P2. So we're just going to write that down. P1 equal to P2. So let's find what P1 is. So remember, pressure is force per unit area. So we have the force at 1 over the area at 1. Well, we know what the force at 1 is. That's 50 newtons. The area at 1, we're going to have to do a little math. So if we remember the area of a circle, because remember we said these were circular, is pi r squared. Be careful, I gave you the diameter and not the radius. So the radius, remember, is just half the diameter, just basic 10th grade geometry. So we know that the area of 1 must be pi times 5/2 squared. Don't forget the square. Similarly, while we're at it, we can just say the area at 2 must be pi times 60/2 quantity squared. So now we're getting somewhere. So if we know these quantities, then we can say that since the pressures are equal, we know that P1 is P2. Well, here's P1. P2, by the way, should be no surprise, should be F2 over A2. We're trying to find F2. A2 we just found is pi times 60/2 quantity squared. If both of these are equal, if P1 equals P2, then F1 over A1 must be equal F2 over A2, right? Well, what are we trying to find? We're trying to find F2. So a little bit of algebraic manipulation gives us F2 equals F1 A1, or sorry, F1 A2 over A1. Now it's simple, right? So F2 is whatever F1 is, that's 50 newtons. A2 we know is pi times 60/2 quantity squared. And A1 we know is pi times 5/2 quantity squared. So if we do the math there, we find that we have an output force of 7,200 newtons. That's a lot. I don't remember the conversion from newtons to pounds off the top of my head. So 1 Newton is about 0.22 pounds, about a quarter of a pound. So that means that 50 newtons, that's about 11 pounds. So 50 newtons is about 11 pounds. This is a small cat, about a 10-pound cat, right? So what we're saying is that if we have a 5-centimeter diameter platform and we put a 5-pound cat on top of it, and we connect to a 60-centimeter platform, Then our output force, because of hydraulic pressure, works out to be 7,200 newtons. That's about 1,600 pounds. That's a lot. This is a small car. So it doesn't take much force in order for us to create a big output force. This is the value of Pascal's principle. Again, because we know that the pressure here has got to be the same. We can do another interesting problem with Pascal here. So think about this. You have, let's say you take your car and you drive your car into the Arkansas River because you've just spent too many hours looking at my physics problems and have decided that you've had enough of life. So you drive your car into the Arkansas River. Your car is probably going to sink. Your car weighs, I don't know, roughly 2,000 pounds. Well, if that's the case, and a 2,000-pound car is going to sink, then how do cruise ships work? How do aircraft carriers work? How do these big barges out there work? They seem to not sink. So something's going on. So we're going to go back to just our general physics principles. We're going to go back to Newton's laws. Everything we're doing here is Newton's laws, right? So we know, let's say that we have water and we have a boat, and that boat has some weight, whatever it is. Let's put a sail on that just so you know it's a boat. Because that's what makes the difference in my art, right? Oh, it's got a sail, now I know it's a boat. So I have some weight of this boat. Obviously, it's going to want to sink. I think the boat is probably far more dense than the water. Especially if it's something like an aircraft carrier, it's made of steel and aluminum. That's certainly going to be far more dense than water. So that implies that since there is this force, the boat pushing down on the water, there must be some force of the water pushing on the boat. That's what Newton's third law tells me. That force is what we call buoyancy. So buoyancy is the force that makes things float. If we think about buoyancy, we think about something floating. It should not be too much of a stretch for you to discern that one of the things that causes something to float or sink has got to be the density of the object. If you throw a square-inch brick of lead into a pond, it's going to sink. If you throw a square-inch brick of styrofoam into the lake, it's going to float. Well, if everything about those things are similar except for their density, then density must have something to do with it. So I have an example here. We're going to talk about this. So let's say that we have a basketball and it has a mass of about 100 grams. Draw this. So here's our basketball floating in water. And it's got a mass of about 100 grams. And let's say mass here. And let's say its volume is about 4 liters. So think of a 3-liter Pepsi bottle, right? So a little bit bigger than that. It's the volume of air. It's going to be tied to a mass of some kind, say it's a bag of rocks. And that bag of rocks weighs 8 kilograms. That's a lot, right? So we've got a basketball that weighs 100 kilograms, but it's 100 grams. Sorry. It's 100 grams, but it's being pulled down by something that weighs 8 kilograms. So thousands of times more mass. So what I want to know is, what is the buoyant force of the bag? Well, we're going to assume neutral buoyancy, okay? So what we're going to assume here is that the buoyant force, whatever's pushing up on the ball, is going to be equal to the weight of this whole system. If they were not equal, you'd have a problem, right? If they were not equal, this would either be coming up out of the water or it would be sinking to the bottom. So we set up a system where we have what's called neutral buoyancy, where this thing, this whole system, this big heavy bag and the basketball are just floating, just staying right where they are. There's no reason that this has to be exactly at the water line, by the way. We can easily put the water up here and we can just make this thing float. This is a useful principle. We use this all the time in training for missions on the space station. Down in Houston, Texas, at Johnson Space Flight Center, they have the neutral buoyancy lab. It's basically just a big giant swimming pool. They fill it with water and they sink replicas of pieces of the space station or a telescope or something down there that the astronauts might want to work on. They put them in their spacesuits. They inflate the spacesuit with air so that they can breathe until such a point that the buoyant force is equal to the weight of the astronaut. They're neutrally buoyant. So now they can effectively float just like they do in space. And so this is a way to train, is to go neutrally buoyant. So we want to know what the buoyant force on this bag is going to be. So we know that those forces have to be balanced. So grams. So we know that the basketball displaces 4 liters of water. Okay, that's going to be key to this. We know there's an upward force of 4 kilograms times 10 meters per second squared. So where the hell did we get that? There's going to be an upward force well, if this thing is neutrally buoyant, then half of that force, because there's 2 objects on this bag, right, has to be half. So half the force would be half the mass, right? 4 kilograms. We're going to assume the acceleration due to gravity is 10, just to make the math easy. The basketball, we know, is exerting some downward force. Well, what do we know about the basketball? That it's got 100 grams of weight. So that's going to be 0.1 kilograms. So this is going to be 0.1 kilograms times our 10 per second squared. And so what we find is that the upward force, the bag, that's going to be 40 newtons. And the downward force, because of the basketball, is going to be 1 Newton. So, what does that mean? That means that the net force acting on the basketball, right? It's got to counter that. It's got to be the difference between the two. So that net force is 39 newtons. Oh, sorry. I did that wrong. Right numbers, wrong explanation. Sorry. We need to know this 4 kilograms comes from the mass of the air inside there. Sorry. So that's 4 kilograms. It's got to push up on, right? Because we got to push against the weight of the air. We know it's 4 liters. The density of the air is 1 kilogram per liter. Right? So density of air is 1 kilogram per liter. We have 4 liters, right? So 4 times 1 gives us 4 kilograms. So that's the mass of the air. So we know we have to push up with 40 newtons of force. And we know the weight of the ball, the basketball, has got to be its mass, 100 grams, so we convert kilograms, 0.1, times the acceleration due to gravity. So the total net force is still going to be in the upward direction, right? Because now we need our vectors. That's going to be down. So Newton's second law tells me sum of the forces. That's going to be our -1 Newton plus 40 newtons. So our net force is 39 newtons. Why do I care? Well, let's now look at the bag. The bag of rocks, we know, has mass, right? It has 80 kilograms of mass. So its weight has got to be 8 times the acceleration due to gravity, which are 10. So that's our 80 newtons, is our weight force of the bag. So in order to maintain neutral buoyancy, then that means the net force has got to be 0. So the bag has got to contribute a force that's got to balance this. Well, this is our negative direction, right? So again, the sum of our forces equals our 39 newtons minus our 80 newtons. And that works out to be 41 newtons. That's our balancing force. That's the buoyancy force. That's how much the bag has got to contribute. So, how does this answer the problem of the aircraft carrier or the cruise ship? What was the key thing? Key thing here was volume. So if we take a look at our basketball, so we've got some basketball shaped object. It's relatively light and it's hollow. It's filled with air. Air doesn't weigh too much. So let's take a look at our aircraft carrier though. So our aircraft carrier looks something like this. You basically get a wedge with a flat part on top. You got the bridge, conning tower, and all that. So inside the aircraft carrier are multiple decks, hangars, living quarters, all that kind of stuff. If you've never seen one of these things up close, I recommend going to Norfolk, Virginia, or San Diego, California is another port for these guys. And check them out when they come in. These things are massive. They're insanely big. And we're about to find out why. So think about the mass of this aircraft carrier. This thing is made of steel and aluminum. It's carrying aircraft, people, bombs, food, anything you would need, right? This is basically a city at sea. So that's a whole lot of weight. Well, the ocean has got to provide some buoyant force that's equal to the weight of this thing. Well, we know that this thing is got some volume and all the stuff in it has some density. So it's not air anymore. Air is our 1 kilogram per liter. Well, we'd have to figure out how many liters of space are in here, but we'd find an average density of this thing. But we do the same thing. We say that our density of the thing times its volume will give you something, right? Well, what's density times volume? Density is mass per volume. If we multiply that by volume, volumes cancel. Hey, look, we get the mass back. So if we know the mass of the aircraft carrier, we can work backwards and find out what the volume of the space needs to be. And we have to set this equal to whatever the buoyant force is, just like we just did with the basketball problem. The buoyant force of the ocean is pretty easy. We know the density of seawater. So if our density of seawater is that. So what are we going to find? We're going to find H. It's going to be the depth that we sink into the water for this thing to float. And so what you'll find on your typical aircraft carrier, cruise ship kind of thing, is that this thing sits way high above the water. This thing sits up probably 100 feet above the water or so. Below the water is probably another 80 feet or so. It's a lot. But these things are exceptionally wide. They're very long. The flight deck on these things is about 1/4 to a 1/2 mile long. So give you kind of a sense of scale of these things. So that's how large ships work. That's why you'll see, if you look out on the river and you have these big cargo barges, that they tend to be these big, wide, flat things. The heavier something has to be, or the more weight it has to carry on the ocean, it will tend to be wider. because it's a function of area, right? So we want to spread the area out as much as possible. Balance our forces. So that's our buoyant force. I think that's where I'm going to stop for today. And what I'm going to go into Friday, the next lecture, I'm going to do a derivation for you of something called Bernoulli's principle. Bernoulli's principle is why airplanes fly. And I think it does a really nice job of bringing these concepts of balancing forces and densities and pressures. It brings all this together very, very nicely. And ends up with a really interesting and surprising result. So that's where I'm going to stop. I will pick up with that on Friday. I will get tests graded as quickly as I can. I'm going to go throw up some homework assignments here in a few minutes. I'll give you until probably the end of next week to get the homeworks done. Shouldn't be anything crazy. So as always, if you have problems, if you got questions, reach out to me, come by my office, and we'll take care of it. And I will see you guys in the next lecture.